Welcome to Chapter 3, Matrix Operations and Systems of Linear Equations. In this chapter, we will talk about solving a system of linear equations. And this will be quite useful for the rest of our financial applications, especially when we talk about the portfolio optimization problem. One of the fundamental techniques that we can use to solve a system of linear equations is the Gaussian elimination technique. If we have a problem such as a times x equals to y, so here actually a is a matrix of coefficients. You can see in this simple example we have a 3 by 3 matrix A, and then x is the vector of unknowns that you would like to solve this equation for, and you have the right hand side which is given by this vector y. So if you want to solve this x in this system of linear equations, you can do Gaussian elimination, which is simply using the row or column operations in order to get zeros in the off-diagonal terms here so that we can solve for x3, x2, and x1 easily. So if we look at this example here, if we consider the first row and if we add that to the third one, what do you get is a 0 here and then -1 and then you have 1. So now you can consider multiplying the first row by 2 and subtracting from the second row here. And in that case, you can also get this term equal to 0, and then you have -2, and you have 1. Now, the third step is to eliminate this term and make it equal to 0. In order to do that, you can divide the second row here by 2, and you can subtract from the third row. And in that case, you get a 0 here as well. Dividing this by 2 and subtracting from the last term 1, you get a 1/2. This way, we get off the diagonal terms equal to 0, and we can easily obtain the solution for x3, x2, and x1. Here, don't forget that the same row operations should also apply to your right-hand side of the equation. So if we do this for this example, you can verify that the solution is x3 equals to 1, x2 equals to -1, and x1 equals to 1 as the solution of the system of equations. However, notice that Gaussian elimination algorithm is computationally not efficient, and it requires in the order of n cubed number of operations. And therefore, we would like to introduce the LU decomposition method. If you look at this simple example, if we can somehow decompose our coefficient matrix, which is in this case a 2 by 2 matrix, in terms of a lower triangular and upper triangular 2 by 2 matrix, then this will significantly speed up the Gaussian elimination algorithm. So in MATLAB, this is not difficult to achieve. We can use this LU function, which is a built-in function in MATLAB. And if we input the coefficient matrix A, remember we are interested in solving a system of equations, and the coefficient matrix is given by this A. So if we input that to our LU decomposition function, it's going to produce us the lower triangular. So here the lower, we have the upper triangular matrix, and we have the so-called permutation matrix as well. So what it does is simply L times U equals to permutation matrix times A. So MATLAB's built-in LU decomposition function simply produces this factorization L times U, which is equal to the P times A. So how we can apply the LU decomposition method to solve a system of equations? Now we will consider a two-step procedure in order to solve this problem efficiently. Notice that our original problem, if we multiply both sides by this projected permutation matrix, P, then what we get is PAX equals to P times Y. But notice that P times A can be substituted by L times U. And if we do that, we get L times U equals L times Ux equals to P times Y. So now, if we consider this nested equation here, U times X, let this be equal to Z, and we can handle this in two steps. So first, we can solve the equation L times Z equals to P times Y, and in MATLAB, Gaussian elimination method corresponds to this backslash operator here. So this is simply the Gaussian elimination method which uses this backslash operator. So once we are able to get Z, this Z now can be used in this inner equation, which is U times X equals to Z. So the same Gaussian elimination can be utilized in this step, and the solution for X can be obtained as U backslash Z. So finally, combining these two steps in one line of code, we can write the solution of this system of equations as U backslash L backslash P times Y.